Is that email into the group? Who is the lecturer? There's no any other course. Let me get detail for the next door lecture and then come back. Okay. So what you do? So last time, where we stop? Okay, let me go into our class first, and then I go to the next door, ask for detail. Okay, let's do some quick revision here. Joshua not back yet. Does Joshua know? Can someone send to the group that we are here now? Huh? Okay, so last time we have these axiom for real numbers. So we have introduced field axiom and order axiom. Okay, so basically field axiom is like group axiom. Okay, so there are two kind of operation here: addition and multiplication. Both of these they form groups. Okay. And then from this axiom, last time we do some group discussion, right? To prove all these consequences, right? Why can you do like minus minus plus, minus plus minus, plus minus minus inside your arithmetic? Because of the field axiom. Okay. And then we introduce this order axiom. So how do we introduce this order axiom? So we don't really care what is less than or equal means for the moment. We just care that less than and equal have to satisfy this property. Okay. Do you still remember if there's some relation that's reflexive, anti-symmetric, and transitive, what do you call it? Sorry? No, equivalence, right? Equivalence is symmetric, but here is anti-symmetric. So what kind of ordering you get? Partial ordering. Then you get partial ordering. Yeah. So actually this less than or equal to is a partial order. Okay. And then this partial order plus with this order preserving property. And also the trichotomy. Okay. But my claim is that no matter how you define this less than or equal to, okay, the claim is 1 is greater than 0. Okay, this is where we stopped last time. Okay. And last time I present a false proof to you, right? I said, let's say we assume 1 is less than 0. Then I can multiply 0 on both sides. And then I get 0 greater than 0, which is a contradiction because 0 equal to 0. Hello, Joshua. Right. So this is a contradiction. Why? This is a false proof. Why? Because in the order preserving property, right, what you get is less than or equal to. Okay, let me come back to this order preserving property here. So if you look closely here, right, if A is less than or equal to B and C greater or equal to 0, what do you get is AC less than or equal to BC. It doesn't say need to be strictly less than or equal. Either one true is okay. Okay, so it turns out that although 0 is not less than 0, but 0 is equal to 0. So it doesn't contradict the order preserving property. So we still need to come up with a way to prove 1 greater than 0. Okay, so can you try and discuss with your friend how to prove 1 greater than 0 using this order property? Maybe for 3 to 5 minutes. I ask about the detail, I'll come back. Okay, try and discuss with your friend. From here, okay, how to prove 1 is greater than 0. No matter how you define greater, okay, but follow from this axiom, 1 have to be greater than 0. Okay, this is the claim. Okay, try and discuss with your friend. I go to the next door, ask for detail, and then I'll come back. Okay. 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 So yeah, last time we were stuck because we don't have enough tool to produce the contradiction. Okay. Actually, we need about at least for my proof now, I need 3 statements that I need to have to construct this contradiction. Okay. So let's see how this 3 statement will help us. So first, I want to prove that if A is greater than 0, then minus A is less than 0. Is this familiar or not? A greater than 0 minus A is less than 0. Is this familiar? Is this what you do? Right, in your calculation. So now we're going to prove it. Okay, why A greater than 0 minus A have to be less than 0? For example, 2. 2 is greater than 0, right? Minus 2 is less than 0. So why when you multiply by minus the inequality swap? Okay. Okay, why is swap? So we prove by contradiction here. Okay. So if I know A greater than 0 minus A, how many possibilities can I compare to 0? Trichotomy law. How many possibilities? 3 possibilities. So minus A have to be equal to 0, less than 0, or greater than 0. If it is less than 0, then we are done. So we need to argue that minus A cannot be 0 and cannot be greater than 0. Okay. So suppose it is equal to 0. Okay. If it is equal to 0, then minus A last time, what we can do, we can multiply minus 1 on both sides. Right. But what is minus 1 times minus A? Last time we proved that minus A is what? Minus 1 times A. And then minus 1 is the inverse of minus 1. Okay, so -1 times -1 is 1. So 1 times A is A. So A equals 0. But we start with A is strictly greater than 0. So contradiction. Okay, so cannot be equal to 0. Okay, minus A. How about minus A greater than 0? Okay. If minus A is greater than 0, A is also greater than 0. Okay, so if I add A to both sides, the order still preserved. So that means I'll get A is less than equal to 0. Does that make sense? I start with minus A equals 0. I add A to both sides. Right. Minus A plus A is what? 0. 0 plus A, because 0 is the additive identity. Minus A is the additive inverse of A. Okay, so I get 0 greater or equal to A. But I start with A is greater than 0. Another contradiction. Okay, so these two cases will give you contradiction. So by trichotomy law, there's only one possibility left. Minus A is less than 0. Okay? Does it make sense? Yes.
Bigger and equal to
Which one?
minus A plus A.
Oh, you mean why this one? This one? This is true. So coming back from this ordering axiom here. So if A is less than or equal to B, this implies that A plus C is less than or equal to B plus C. So you keep this less than or. Just now. Which one? Yeah. Correct. Oh, don't have the equal sign, huh? I mean, this statement. Okay, so you see this statement, right? There are two. Okay, so here is P implies Q, right? Inside P, there's a or here. Inside Q, there's a or here. Okay. So it doesn't say that if this is strictly less than, then this follows strictly less than. It's not like that. Because this is exactly the false proof we did last time. Remember? The false proof we did last time? Yeah. So you really get the whole statement less than or equal to. We don't know which one is true. Because for the whole statement to be true, either one of the or true is true. Right? Okay. Okay. So if you want to prove a stronger statement, okay, if it is strictly, then it is strictly, then you need to prove a stronger statement. You know what I mean? If you want to turn this into a strict, if you want to turn this into a strict inequality, then you need to prove it. For the axiom, it just gives you either greater or equal. Don't know which one. Yeah. Okay. If you want to say that this is strictly greater, then you need to prove it. Okay. Okay. Yeah. Okay. Yeah. Right. And then it's about this closure of positivity under addition. So if you add two things that is greater than 0, the addition is also greater than 0. Okay, we need to prove it. It's not entirely clear why it is true. Although it is true for natural number, right? Natural number you cannot go backward one. But real number, I don't know, because this is like a new thing we created. Yeah, just by few axiom or the axiom. But how do I know that if something is greater than 0, then you add the two things must be greater than 0? Can it be negative or not? Or can it disappear or not? Go to 0 or not? Okay, so we prove it. It must be strictly greater than 0. Okay, how we prove it? Same concept. If you want to compare to 0, there are only 3 possibilities. What is the 3 possibility? Yes, bigger, equal, or less than. Okay, so you need to show that less than and equal doesn't happen. Then by trichonomial greater have to happen. Then greater than 0 have to happen. So first, I suppose A plus B is 0. Okay, if A plus B is 0, right, implies what? A equals to minus B. So you see, since A equals 0, A is greater than 0, minus B also greater than 0. But from the previous proposition says what? If I multiply a minus to minus B, I will swap the inequality. B is less than 0. But I start with B is greater than 0. Contradiction. Okay. So A plus B cannot be 0. Okay. How about the other case? Can A and B less than 0 or not? Okay, suppose it is less than 0. What happened? Okay, I can add minus B on both sides. In this case, minus B is greater than A. Okay. But minus B greater than A means what? A is also greater than 0. Okay. So by transitivity means what? Minus B has to be greater or equal to 0. So transitivity says what? Okay, come back here. If A less than or equal to B, B less than or equal to C, then A less than or equal to C. Okay, so transitive. So you get minus B is greater or equal to 0. Meaning what? B is less than or equal to 0. Again, contradiction, right? B cannot be 0 because B is strictly greater than 0. B cannot be less than 0 because B is greater than 0. So it cannot happen. Okay, cannot happen. Does it make sense? Okay, try go back and practice this proof. Look at this proof. Okay, try and write out yourself. This one is very simple contradiction proof. So you make sure you can get it. Okay. So here is by the transitivity. Okay. Sorry. I don't think so. Why? Huh? Can you do direct proof? How do you do that direct proof?
That's because I'm supposing to three stage. The first one is to prove when A is smaller than B, the negative B is smaller than negative A.
Okay, wait, let me see what are you trying to say. Again, so suppose A is greater than 0.
And A is smaller than B.
Oh, okay, when A is okay, so either A equals to B, either A less than B, or either A greater than B, right? So three possibility.
Also consider case A less than B. Oh, just A is smaller than B, just right. Like when A is smaller or equal to B.
In this case, yeah. Okay. Plus and equal. Okay.
You can from this you can happen. You can find negative B is smaller or equal to A. Negative A.
Okay, so from here I will get minus B is smaller than negative A. Sure. Have we proved this yet? Yeah, we need to prove this. Okay, so let's say you already proved this. Okay, this become a lemma. Okay, then
Is smaller than 0 smaller than C. AC is smaller than BC.
When C is
When A is smaller than B
and
C is greater than 0.
Okay,
AC is smaller than BC.
and C is smaller than BC.
Actually, C can equal to B0 and AC can be equal to B.
Wait, talk a bit slower. Oh, okay. C less greater or equal to 0, and then sure. Wait, this one is the order preserving property, right? Okay, sure. And then property.
Yeah, find when A is equal to 0, you can find BC is bigger than 0, B comes C.
And then
And use these two lemma, you can find A squared is always bigger than 0, whatever A is.
and then
Yeah, when A squared is bigger.
I want to prove A plus B is greater than 0, right?
Yeah, but well, later. Yeah.
What are you trying to do? Why you have a C coming in? I want to prove A plus B is greater than 0.
Okay. Let's move on.
Okay. So I mean, if you want to prove direct proof, right? So there are like 3 cases you need to take care, right? You need to either A goes to B, A is less than B, or A is greater than B. You need to discuss all these cases. Okay, you need to discuss all these cases. Okay, if you want to do direct proof, I'm not sure it is possible or not, but yeah. Okay. Similarly, you show that it is closed under a closure of positivity under multiplication. Okay, so meaning if you have 2 positive things, okay, greater than 0, then the product is also greater than 0. Same proof, use contradiction. AB cannot be equal to 0. AB cannot be less than 0. Okay, that will be contradiction. So my claim is with this 3 proposition here, I can prove 1 is greater than 0. Okay. So how to do this? So claim 1 greater than 0. So first we know that 1 cannot be equal to 0. Okay. So why 1 cannot be equal to 0? I give you a very serious problem here. If 1 equal to 0, you know what will happen? You know what will happen? If 1 equal to 0, your real number is just a set with 0. There's nothing inside. Your ring, your field collapse into one thing. Okay, let me show you. So if I have 1 equals 0, what does it mean? 1 is the thing that act like an identity, okay, under multiplication. 0 act as an identity under addition. Okay. So if you say that 1 equals 0, what will happen? You take any real number, you start with any real number. Anything in my set real. I don't know what is the thing. But A surely equals to A times 1. Last time we proved already. I mean, this is definition. But 1 equals 0. So this thing is equal to 1 times 0. But last time we proved 1 times 0 is what? 0. So everything is 0. So inside your set, there's only 0. So this is not an interesting set to look at. Okay, so we need to require 1 is not equal to 0 to build the field. So this claim here, we know that 1 is not 0. So there are only 2 possibilities now. Either 1 greater than 0 or 1 less than 0. If 1 greater than 0, then we're done. This is our claim. Okay, so suppose 1 is less than 0. Or we just now prove already. If I multiply minus on both sides, then I swap the inequality. Minus 1 is greater than 0. So I got something that is greater than 0 now. Okay, minus 1 is greater than 0. But notice that 1 is what? Minus 1. Last time we proved, right? Minus A is A. But minus 1 is what? I can pull this minus 1 out again. Minus this minus is inverse of a minus 1. Okay, but now we make it into a number. This inverse, I make it into minus 1. Last time I proved, right? Minus 1 times A is just the inverse of A. So minus 1 times minus 1. But minus 1 times minus 1 is what? 2 things that is greater than 0. You multiply them together. This thing is still going to be greater than 0. So in this case here, you have 1 greater than 0, 1 less than 0. 1 greater than 0 is the negation of 1 less than 0. So there's a contradiction here. Okay, so 1 less than 0 cannot happen. Okay, so 1 have to be greater than 0. Does it make sense? Okay. So we are trying to be quite rigorous here. Rigorous means we need to ask ourselves, why one have to be greater than 0? And one less than 0 no? Okay, in our case cannot. Okay, with the order axiom we have, cannot. Okay, one have to be greater than 0. For now, what do you know about one? Jing Shen? What do you know about one? No. What's the property of one? What does one do? Okay, before this, what do you know about 0? 1. Before this, greater than 0. How we define this 1? How we define this one? Yes. So this is the multiplicative identity. It's not the one thing one, not this thing. Not one bottle, one book, one computer, not this one. It's the thing that when you multiply to it, you get the thing back. Okay, get the number that you multiply back. Okay. So it's the additive identity. So here what I showed is the multiplicative identity is greater than the additive identity. That's all. Okay, you don't know what is 0. You don't know. You know this is a 0 thing. This is a 1 thing. No, not like that. Okay. Does it make sense? From algebraic structure, okay, we deduce their order. Okay. Can everyone accept this concept or not? Can okay. Because later we're gonna make do some cool things. Okay, how we construct our number system. And the corollary is 1 plus 1 is not 0. Okay, you don't go back to 0. You create another thing. So how do I prove this? I know that 1 is greater than 0 now. So 1 plus 1 is greater than 1 because I can add 1 to both sides. I think should we do greater or equal to, because this is what the axiom gives us, greater or equal to. But so now we show that 1 is strictly greater than 0. And so by transitivity, then we can see that 1 plus 1 is greater than 0, okay, which is not 0. Okay, so 1 plus 1 is not 0 in this world, so that we don't collapse too fast. Okay, in what world 1 plus 1 is 0? Modulo? Modulo what? Sorry? Modulo minus 1? No. In what world 1 plus 1 is 0? Modulo? Modulo 2? Yeah. Okay. 1 plus 1 is defined to be 2. So if I modulo 2, then 2 equals 0. Okay. Yeah. Sorry? Why? Why was it? Yeah. So where is it applied? No. Why suddenly come up with the statement? Oh, you mean like, you mean 1, 1, 0 is like true, false. Oh, okay. Sure. Okay. Yeah. Good. Okay. So, yeah, we got 1 plus 1 is not 0. Any question about this? About this thing here? Any question? So your mind, some people say when you go deep into mathematics, you get crazy. I don't agree. I certainly don't agree. Okay, why you get crazy? Some people try and argue why people say if you study mathematics, you get crazy. Can you try and argue why they say so? I don't agree, but I need to know why they think like that, right? So why they say so? You see, just now is my statement confusing or not? I say 1 is the multiple identity, but it's not the usual one that you think about. Is it confusing or not? It is confusing at first. But what we are trying to do is we want to split out the property that this one that gives us. It's like I want to know about Seng. I cannot just know about her long hair. I also need to know about her ping pong skill, right? You get what I mean? Okay. So I study Seng, maybe I first study her ping pong skill. Okay, like how learn ping pong from her, right? So he knows Seng from her ping pong, how to say, ping pong, maybe, ping pong, how to say, the ping pong aura, okay, from Seng, right? But Seng, when she is not playing ping pong, she's another person, right? Is it true?
Is it true?
Is it true? So you see Seng from different faces. Okay, this is what mathematics trying to do. Can we just use ping pong to reconstruct Seng or not? Okay, can we study from her ping pong skill that know how this person be when she is in different field? Right? Is it possible or not? This is what mathematics is trying to do. Okay. Okay. Yeah. So let's continue with new stuff today. All right. So seems like greater strict equality is very important here. So we will define this strict equality. So when is A is strictly equal to B? Strictly greater than B. Okay. When is A less than B? Okay. So we will define that S is greater than B if what? If I have more money than Ethan, what does it mean? I'm richer than you. So yeah, yeah, this is the answer I want. But this means what? If we cancel our asset, right? I still have something else, but you don't have nothing more already. So meaning A minus B have to be greater than 0. Okay. If A is less than B, meaning the other direction work. Okay. B minus A is greater than 0. Or in other words, minus A minus B. Okay. And so in here, right, although this is an inverse of A minus B, but in your mind, you have to swap. Actually, it's -1 times A minus B. Okay, so you need to freely swap between inverse and -1 times the element. Okay, you need to freely swap between this. And greater equal to B, this one is what we defined before. Less than equal to B, also what we defined before. Okay, less than or equal to, greater or equal to. But now we define what is the strict inequality. Okay, so why I do this? Because we will have some more proposition from order axiom. So let's run through it first, and then we will see which one we want to prove. So if A less than B, right? If C less than 0, if I multiply C to both sides, what do you get? You will swap the inequality. Okay, this is a very standard thing. And 2 is what we have proven already. If 1 greater than 0, you multiply -1 to both sides, and then you swap the inequality as well. How about if you take the inverse of a non-zero element? Okay, you still keep the inequality. For example, 2 is greater than 0. 1/2 also greater than 0. Okay, so I need to prove. And similarly, if you have B greater than 0, A and greater than 0, you will get 1/A greater than 1/B greater than 0. So you swap the order of the inverse of A and B. Okay. This one makes sense, right? How you remember last time your teacher, how you asked you to remember? Because you divide by a denominator which is larger. Right? So you need to prove using the order axiom. Why is this true? Actually, the fifth one is the most important thing throughout this course. You're going to use this. You have to memorize this. This is a triangle inequality. Okay, triangle inequality means wait, I think I put something wrong here. So should be the length of A plus B is less than or equal to the length of A plus the length of B. Why is this called a triangle inequality? Does anyone know? Where's the triangle? Yeah, where's the triangle? How to form a triangle here? Yeah, well, yeah. How to form this triangle here?
Those and connected.
Take three angles and connect. I mean, how these A and B represent what part of triangle? 变长 side. Side, yes, side of the triangle. So you should imagine like, okay, this is maybe here. So A and B should form a side of a triangle, two sides of triangle, and then A plus B should be the hypotenuse. This. Okay. C square equals to what? A square plus B square, but this is for a right angle triangle, right? So meaning what? Meaning what? Does it mean anything or not? So let me draw this A squared equals to B squared, C squared thing. Oh, there's a formula for this right angle triangle, right? So this one will give us C squared equals to A squared. Okay. So the distance between these two, x1 and x2, right? What's the shortest distance here? The shortest distance actually is the straight line, C. Okay, this is the shortest straight line. If you go through A and then go through B, this A plus B should be greater or equal to C. Okay. Yeah. Okay. So this is how you should relate this to triangle. Okay. So you can think of A and B as the side of triangle. But there's a bug here. Where's the bug? Because this A and B is in R2, but this A and B is in R. Okay. So can you think of a way that when A plus B, okay, is strictly, if you after you take modulus, is strictly less than the modulus of A plus modulus of B? Can you think of an example? So let's try and think an example. Find AB such that A plus B modulus is strictly less than modulus of A. Okay, I give you 2 minutes. Talk with your friend. And find AB such that this is true. Strictly. Find AB. Now talk to the friend beside you. Find AB such that this strict inequality happens. Equal is quite easy, right? Maybe you can find, if you don't think that it's easy, try and find one for equal as well. Yeah. So find one example for equal, find one example for strictly. Oh, example, Seng. Right, what's AB? Give me A and B. A should be what? A2. Okay, Jack pick 2. Can you pick one or not? Can you pick one for B? Seng, can you pick one for B such that this is true? -2. Okay, good. So let me try. So let us try this example. Okay. So on one side you have 2 plus -2. What do you get? 0. Okay, modulo of 0, you still get 0. Okay. So actually I should define modulus for you, right? Do you still remember what is modulus mean or not? Do you guys still remember what is modulus mean? What does modulus A means? No, wait. Modulus A means what? What's the definition of modulus A? Do you remember? A, when A is already large than greater than 0, minus A if A is less than or equal to 0. Okay. So I solve it. Okay. But on the other side, I have modulus 2 plus modulus -2, which is what? 2 meaning already 2, so I take 2. But modulus -2 is less than 0, so I need to take minus 2. So I get 2. Okay. So which is 4? Yes. So 4 is strictly greater than 0. Okay, good. Just how fun you say equal maybe not so easy also, right? So can you find A, B such as easily? So okay, never mind. It's fine. So what is the example for the equal sign to hold? Yeah. Yeah, as long as A and B greater than 0, then the equality will hold. A and B smaller than 0. Yeah, it's also the same. Yes, that's right. Prove it. Try and prove it. Yeah, prove it. You should prove it. Okay, you should prove it. But we will prove it now for this triangle inequality. So I will use this lemma here. First, I prove a stronger segment. So this is typically what we do. Sometimes we did in pure max. We prove a stronger segment, and then we deduce from a stronger segment. So the stronger segment here is if A and B are positive, okay, and P is some natural number, B strictly greater than A, if and only if the P power of them also follow the same order. Okay, how should I prove this? How should I prove this? B greater than 0 means what? I have more money than you, right? So my difference is positive. So I need to prove that. Okay, so which direction? So actually we prove if and only if here. So let's study what is BP minus AP. Okay, if we want BP greater than AP means what? BP minus AP have to be greater than 0. Okay, good. But what is BP minus AP? I can do this factorization here. Can I? Correct or not? This factorization. Okay, this factorization is correct. But minus B minus A here is about this guy, right? Okay, if this thing is greater than 0, then we will have B greater than A. But how about this guy here? What is this guy here? B is positive. A is positive. You are taking power of positive number. Still positive, right? You are adding positive number. Still positive. So this side here is always positive. Okay? So meaning what? Meaning these two sign here depend on each other. If B minus A is positive, then the left-hand side is positive. If the left-hand side is positive, then the right-hand side is positive. So it is an if and only if. Okay. Yes, so far so good. Yeah. So how we apply this lemma here? So we just apply when P equals to 2. Okay. We apply P equals to 2. So how do we apply P equals to 2 here? So we start with this that we want to prove here. Okay. this is true if and only if you squaring both sides is true. Make sense? This is what we have proven. So here, let me put by lemma. This part is by lemma. Okay. Okay. Then we could expand this power here. Okay, I will get a squared plus 2ab plus b squared less than or equal to a squared plus 2 absolute value of a times absolute value of b plus b squared. Okay. And then in the end, I get 2ab is less than equals to 2 times absolute value of a and b. Is this always true or not? The last line here. Is this always true? So this has to be true for what? For a and b, arbitrary. Okay, arbitrary. Any a and b. Is it true or not? True, right? Because on the right-hand side here, this is always positive. If a, b positive, then they are equal. If one of the a or one of the b is negative, then you get, maybe you get strictly. You might get equal to if one of them is 0. Because 0 equals 0. Okay, so this is always true. Okay. Okay, yeah. So, yeah, try and read this proof again. And this result is really important. Absolute value of a plus b is less than or equal to absolute value of a plus absolute value of b. So how to remember this? Meaning what? You can split the sum inside here, okay, and then add the absolute value. Right? This is how you should remember it. Does it make sense? Absolute of a plus b, I split the sum into absolute a and absolute b. Okay. How they compare is by this inequality here. Does it make sense? Okay. Okay. And then last one, you also can prove it using similar method in in 5. Okay. But this one less use, but it's also quite useful. Okay, try and prove this. Go on. And the other 1, 2, 3, 4, right, I left as an exercise. This is a similar exercise we did for the field axiom, but now you need to apply the order axiom to prove it. Does it make sense? Okay, yeah. This is a similar short exercise we did last time. Okay. Yeah, so this is about this. Okay, we have introduced a few axiom, order axiom. Any problem before we go to the final axiom, which is the completeness? Any question on order axiom and field axiom here? So you can see that field axiom and order axiom is already quite strong. What do I mean by quite strong? Quite strong. We can already start doing arithmetic, how to add stuff, how to compare two numbers. We get the result 1 greater than 0 and something like that. Okay. But there's a really one very important thing about this real number is it is complete. Okay, so complete in what sense we will discuss later. Okay. Any question before we take a break? Yes. Number 2, what's 2?
1 bigger than 0. Why minus 1 smaller than 0?
This is with proof. Yeah, you can prove by adding -1 to both sides. Yeah. Oh, yeah. Yeah, true. So there will be an equal signs there. So you need to argue why -1 cannot be equal to 0. Does that make sense? But just now I somehow already proved a stronger statement, right? If a is greater than 0, then minus a is less than 0. And this one I proved a stronger statement just now. This statement here. This is stronger. Can you see why is it stronger? If you let a equals to 1, I straight away know -1 is less than 0. No, statement. Don't look at the proof.
Oh.
Look at the statement. So that's why I put color here. when I talk about statement, right, go back to the proposition. Why proposition is true, only look at the proof. Okay, if I'm not talking about proof, then don't look at the proof. Look at the statement only. So this statement says what? If A is greater than 0, minus A is less than 0. So if A is equal to 1, then you will get minus 1 is strictly less than 0. Okay. And why 1 is greater than 0? Also, we prove it, right? That is the claim. 1 is greater than 0. So if true, then the thing behind has to be true. So that the whole sentence is true. Because I proved the whole sentence is true already. Okay. Does it make sense? This is how you apply this proposition. Okay. So just now I say, if you want to prove yourself, maybe you add minus 1 to both sides, and then the order axiom only tell you less than or equal to, right? You need to argue why it doesn't equal. Then in this proof tells you why it cannot be equal. If equal, then actually your A is also 0. So 1 is 0. Contradiction, no? You see? So this is how useful is this proof. Make sense or not? This proof will work for any A. Understand? Okay. Okay. Okay or not? So your proof must contain all cases. Then you will prove the same. Otherwise, you will have gap in your proof. Okay? Okay. Can or not? Okay. Try and write it up. Try and write it up. Hey, after you listen, make sure you write it up. Okay? Make all your cell understand it, not just your brain cell. Okay? Your hand cell also need to understand it. Okay? Okay. So we have covered 2/3 of the definition of real numbers. Then later we're going to completeness. So let's take a break until 12:05. Again, let's take until 12:05. You can take a toilet break. Ethan, where's your friend? Who you with? Let's take attendance. 看野有缘 not here. 金山举家 Ivan holiday. 思颖 Helen Mary Mary 罗浩钟毅小童曾康李欣尹登水妮燕如罗拉潘伟。Which one? One greater than 0.
会。
也不知道好是这样子。
刚好让他跟那一位呢，是不是应该有意思？而且这个是不错的。从我身体，对，这个小人物。
不是，要慢慢加它进去那个。
对，
这样子很重。A S 1，然后 B S。那如果5，应该都
这个零四。
我要先设定，这样是有一个情境。啊，懂吗？方法。我觉得第二次操作的话，这个是还得我发现还是那个。为什么没想？
啊，新眼交通呢？啊，拿寿司。哦，then maybe we don't wait for them then.
Okay, So we're gonna introduce last axiom for real number, which is completeness axiom. But before doing that, we need to deal with some concept first. So first concept is bounded above. Does it sound familiar or not? Bounded above. Okay, bounded above sequence, right? Last time we talked about sequence. Okay, now we don't really care about sequence. We just care about some subset. Okay, non-empty subset of X of our real number. Okay, is bounded above mean what? Do you want to guess or not? What does it mean? Bounded above by M, let's say. If this number is in real number, such that for everything in my set, all the thing is smaller or equal to M. Okay, then this is bounded above by M. Okay, so the set is bounded above by N if everything inside is less than or equal to the M. And in this case here, what do we call this M? This M is called an bound from up. So it's called a upper bound. Upper bound for X. So similarly, you also can define another thing called a lower bound, which is bounded below. So you change the order less than, so it becomes A is greater or equal to, right? So you can try and exercise, define lower bound. Quite important, later in the course we will use it. Because where can you imagine we're using it? In the integration, we'll use it. Because integration, we have upper bound, lower bound. Okay, we'll use both and define lower bound. Okay. Yeah. Question? No question. Okay. So let's do some example then. So let's do some example. So let me give you one set here. How about two set actually? We give you two set here. One is everything in rational such that s squared less than 2 and n is the natural number. So are these two sets bounded above or not? Yeah. Both of them. The second one is what? Is it bounded above or not? No. Why? Sorry? Bounded below. True, it is bounded below. So why is it not bounded above? Why is it not bounded above? For n. How to prove it? Contradiction. Very good. So we want to prove by contradiction. How to prove by contradiction? Suppose it is bounded above. Suppose it is bounded above, right? So this is like how to say 逆向思维. So you need to go the other direction. So suppose it is the bounded above means what? By definition means what? There exists a M in real number such that for everything inside the natural number, X is less than equals to M. Okay. Okay. How do I produce contradiction here? How do I produce a contradiction here? Contradiction means what? they must have some x which is greater than m, so that you have a contradiction. So what x can do the job? M plus 1. Huh? But you think here m is a real number. Real number might not be a natural number. Right? Okay. So we don't have much tool to prove this actually. But if you want to play some tricky trick, is the how we call the floor function, right? Floor, wait, ceiling function. Ceiling define ceiling function. Anyone know what the ceiling function is? What's a ceiling function? So it is a ceiling, first of all. Ceiling takes what? Takes any real numbers to a natural number. So how the ceiling function is defined? It depends on the decimal expansion of R. What does it mean? What's the decimal expansion of R? For every element in R, we can write x equals to A1, maybe dot to A n, and then dot B1 to B m, such that A1, AN, B1, BM is the digit 0, 1, 2, 3, 2, 9. Right? Okay. This is a decimal. This is. Did you guys learn this or not? Ceiling function. Where? Discrete map. Discrete map. Okay. So what's this ceiling function here? So you will send x to A1 dot AN plus 1. Correct? Is this what ceiling do? Yeah, ceiling do this. Floor just take the A1 up to AN part. Right? But ceiling you plus 1. Right? Then you can define your x to be your ceiling of the M. Okay, but this is a bit, I would say, playing cheat because we don't quite know R, but we have this function already, and then. But later we will have a cleaner way to prove this. We will have a cleaner way to prove this statement. Okay, so the claim is here, but if we take x equals to the ceiling of M, then the ceiling is greater than M. So a contradiction. And I would say later we will use a cleaner way to do it. Okay, but intuitively, why n is not bounded above? Because n is keep growing, right? So 100, 1,000, 1 million, and then keep growing. Okay. How about the first example here? Okay. How about this one? Is this bounded above or not? Is this bounded above? Bounded above by what? So if it is bounded above, right, it must have an upper bound. Can be bounded above by what? By 3. 3. Okay, let's say 3. Okay. So can we prove this or not? Okay, how do we prove this? Okay, how do we prove this? So we need to show that for every x in here, x is less than or equals to 3. Okay, so how are we gonna prove this? Any idea how we're gonna prove this? So we're gonna prove by cases. Okay, we're gonna prove by cases. Okay, so let's split A into number that are less than or equal to 1 and number that is greater or equal. Okay, why? We will see that there are different ways to see why they are less than 3. Okay, we'll see that there are different ways to see why it is less than 3. So for example, if your number is already less than or equals to 1, okay, then what? Then obviously what? Okay, it's smaller than 3, sure. Let me think. So, but inside here, if you want to satisfy x squared less than 2, still satisfy, right? Because x squared less than or equal to 1, less than or equal to 2. Okay, sure. This one is in A, and then x is less than 3. Okay, sure. Okay, yeah, good. Correct. Okay. Okay. Obviously, this is true. And it's less than 3. Okay. But is for x greater than 1, how are we going to prove that x is less than 3? Huh? So how are we going to prove x is less than 3? Square both sides. Square both sides. You mean x squared greater or equal to 1? But x squared also is greater than 2. Correct? Because it's A, because x is in A. Then how about x? I want to know something about x, right? I only know that x squared is less than 2. Surely 2 is less than 3. We can deduce from 1 greater than 0. But how about x? Where is x? Yeah, we want to prove that x is less than 3, right? So we want to show that for every x in A, x is less than or equal to 3. So how are we going to show? How x can come into the scene here? This is the reason why I split my s into something less than or equal to 1 and greater than 1. Because if I square anything greater than 1, right, x squared will be greater or equal to x. Is it true? Is it true? True or not? True, right? Okay, so that I can use the chain of inequality here to see that x is actually less than 3 using the transitivity. Does that make sense? Make sense? I cannot apply this. I cannot do this on x less than or equal to 1. No? I don't know. I cannot do that. Because s squared, like 0.1 squared is what? 0.01. Becomes smaller. Only the number that is greater than 1 after you square is greater than the numbers. Okay, so this is why I split the case into 2 cases. Okay or not? Any question? Any question? So I split A into 2 cases. I want to prove that for all x, it is bounded above by 3. So first case, since x is already less than or equal to 1, this modulus means what? This x is actually in between -1 and 1. So already less than 3. So this one obviously true. But this one in this case I'm going to use the property of my set to see that x is actually bounded above by 3. Because I know that x squared is less than 2 to stay in the set. Okay? Yeah. So can you notice something here or not? Can you notice something here? This 3 seems like not unique. Right? Excessive. You mean bound 2? You can take a smaller bound, you mean, right? Can we take a smaller bound than 3 or not? What smaller bound I can take? Huh? 2. 2 also bounded above, right? 2 is greater or equal to x. Can I take smaller than 2 or not? Maybe cannot already. Because otherwise, you cannot make sure that the whole inequality is solved. So here we have a concept of least upper bound. Okay, the smallest one that can bound it. Okay, so let's introduce a new concept here. The least upper bound. Okay, so among all the upper bound, there's the smallest one. We call it a least upper bound. So let's start with a non-empty subset of a real numbers. Okay, a real number m is a least upper bound. Okay, so this is a new concept you have to learn in mathematical analysis before you graduate from this course here. LUB, okay, sometimes we call it, or the supremum. Yeah, supremum. For S, if, okay, two property. First of all, this number have to be an upper bound, right? Least upper bound. It has to be an upper bound first. And then what does the least do? How do you make sure it is the least one? How do you make sure this upper bound is the least upper bound among the upper bound? Means what? 最小的 means what? When you compare to all the other upper bound, it is the smallest. In other words, it is less than or equals to all the other upper bound. Okay, let's say we call it L. Then M is called the sup of X. Right. So let's say I say, oh, in this class, everyone is tall. Everyone is tall. Who is the least tall one? So how you do it? You need to compare to everyone such that it is less than or equal to every other guy. Okay, every other people. Okay, so this is least upper bound. So two property here, least and upper bound. Okay. Okay, so for example, let's give an example here. So let our set be a closed interval 1 to 0. Okay. And we want to prove that 1 is an lowest upper bound for X. Or 1 is the supremum of X. So how to prove it? How to prove this? First of all, you need to prove that it is a upper bound for X. Is it obvious or not? 1 is an upper bound for X. For every number inside here, it is less than or equal to 1. Why? This one is just by definition of the closed interval, because everything inside here is greater or equal to 0 and less than or equal to 1. Okay, so upper bound is easy. How about least upper bound? Okay, it is smaller then all the other. Which one? Yeah. You can write by definition. By definition, for every x in S, okay, S is greater or equal to 0 and less than or equal to 1. So in particular, it is less than or equal to 1. By definition of a closed interval. Yes, true. So I will write here first by definition. Everything in S is less than or equal to 1. Okay, upper bound, quite easy. How about least upper bound? Why is it the least one? It is smaller than all the other upper bound. In other words, means what? Anything below it, any number below 1, it cannot be a upper bound. Okay. So need to prove, okay, to prove 1 is the least upper bound. We must show that if x is less than 1, then there exists y in the set such that x is not the upper bound. Okay, there's something greater than x. Sense or not? Anything below my least upper bound, there's something greater than it. Okay. 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 Meaning you cannot go lower already. You cannot go lower than this bound. Then it is the least one. Okay. So how to do that? So how do I find this y here? So I mean, okay, this is this is a technique for analysis. You need to try and draw it. Draw this set. How to draw this set? 0 to 1, like this. Okay. So S is less than 1. So where should S live? Inside the interval here. Okay, let's call it X. So you need to find some Y that is greater than this X. Okay, so you need to find. So this Y have to be greater than X. So where should the Y live? Between 1 and X is enough. Okay, so you need to somehow find this Y out. Depend on the X. How to find it? How to find? So you need to somehow very, how to say, cleverly use the distance between X and 1. Because we know that X is strictly less than 1. So meaning there's a gap here. Let's call it epsilon. This is why epsilon is created. So there's a epsilon gap there. Can you use this epsilon gap to build your Y or not? Can you use this epsilon to build some Y that is greater than X? Can build or not? How to build? I know how. How to build? I know how to build. So okay, let epsilon to be 1 minus x first. Okay, we know this is greater than 0 already. Okay, how to build Y? How to build a number that is greater than X using epsilon? X. Take Y to be what? How? Think. This is a very important question for later course. Use the gap to build a number that is greater than x. X plus epsilon. X plus epsilon. Sure, you can do that. Can you do that? Yeah, you can do that, right? This one. One is okay, right? So it's okay, right? So let's take y equals to x plus epsilon. Then actually this guy is really just 1, right? But 1 is greater than x. So y greater than x. Yes. But can we do something non-trivial? Do something non-trivial, can or not? We can do something non-trivial, right? So let's say this is y1. Can you pick another number in between 1 and x or not? Yeah, we can scale the epsilon, sure. So what choice you want to make here? Okay, sure. X plus epsilon over 2. So this point here is where? Somewhere in the middle, right? So somewhere in the middle here. Epsilon over 2. Does this work or not? Let's try and compute. Does this work? So this is x plus 1 minus x over 2, which is what? Which is 1 plus x over 2. Is this correct? Correct, huh? Okay. Which is what? Is this greater than x or not? Is this still greater than x? So you need to ask a question whether 1 plus x over 2 greater than x or not. Meaning, is it 1 plus x greater than 2x? Meaning, 1 is greater than x. But 1 is greater than x because we assume it. Okay? Okay. Does it make sense? Because why I do this? Why I do this? Because why I do this? Okay? Because let's say I change my question or I change my question like this. So let me change my question. For example, 2. If I don't have 1 inside my set anymore, I throw it out. Strictly less than 1. Again, prove that 1 is the lowest upper bound. Then I cannot use Lorentz choice already because 1 is not in there already, right? Okay. So I can use the second method I do just now. Okay. Yeah. Yeah. Any question? Any question? Very important, you need to know how to prove that something is a least upper bound. Okay. I give you a set, try and find the least upper bound, and then prove that it is a least upper bound. Okay, this is what you need to learn from here. I think I will put example into the tutorial question and then ask you to try and do. Okay. Does it make sense? Make sense or not? Does it make sense? But the technique here is here, really here. Okay, you need to try and picture this epsilon y thingy. Okay, if I give you an interval, try and draw it out, and then where is this x and y live in? Okay. Okay. This part, the second proof I left as an exercise. Try and imitate the first example and then write it out. If you have problem, and then we can discuss next time. And maybe next class I will prepare some question for you to practice to show this least upper bound example. Okay. Okay. So proposition: if if a subset is bounded above, okay, then what? Then this set actually has a unique upper bound. Okay. Actually, this sorry, unique least upper bound. So actually, least upper bound is unique. Okay. How to prove this? Sorry.
This upper bound required.
Let me think. Okay, existence. Okay, right. Yeah, right. So existence. What's that? Wait. Let me think. How to get this? So. Okay, wait. Let me think. How to formulate this? So my statement here is if I have a least upper bound, if I have then it must be unique. Okay, so I would say here if exists. Okay, so this statement doesn't prove existence. You get what I mean? So I mean, here got two things inside this statement here. Has a unique. So there exists a unique. But Larry was right because we haven't really defined what is real number yet. We don't know whether it exists or not, this thing. But if it exists, it must be unique. Okay, this is what we want to prove here. The uniqueness is there. If it exists. Does it make sense? 很神奇哈，没有的东西这么只有一个嘞。Actually, this is not too how to say, not too. This concept is not too new for you. For example, unicorn. Unique or not? You know what is unicorn? What is unicorn? 独角兽 unique or not? 只有一只吗？全世界 unicorn 有吗？还是一 group unicorn？ 啊，神话里面是一只还是一群？很难讲。OK，let's say 只有一只啦。OK， 存在吗？不存在。但是只有一只哦。OK 啊。Mickey Mouse 存在吗？不存在，有几只？OK， 一女嘛 ，right？ OK，male and female。OK，let's say 就有一个 male Mickey Mouse。OK， 可能他有他 family 啦。But I mean we say about the character 啦 ，the main character Mickey Mouse。OK， 只有一只了。OK，but does it exist 啊？没有 exist 啊。OK，so 这边 ，so here we say that if this upper bound exists for this set, it must be unique. Okay, how to prove this uniqueness? Uniqueness trick is what? Suppose there are two least upper bound, and then we want to prove that they are equal. Okay, so let A and B be two least upper bound for S. We want to show that A equals to B. Okay, how to show this? What's the second property about least upper bound? If A is a least upper bound means what? LUB. Means what? A is less than or equals to every upper bound. But B is also a upper bound. In particular, A is less than equal to B. Right? Okay. Similarly, B is also a least upper bound. Means what? any other upper bound is greater or equal to B. So we get A is less than or equal to B, B is less than or equal to A by the order axiom. A is equal to B. Okay. So you can think about this. So this least property is a uniqueness property. That if it exists, there's only really one guy in exists. It's really unique. Can follow this? Follow this argument, okay? Can follow now. If A is the least upper bound, then it is less than any other upper bound, in particular B. Okay. If B is a least upper bound, it is less than or equal to any other upper bound, in particular A is also an upper bound. So I get A is less than or equal to B, B is less than or equal to A. By the order axiom anti-symmetry, we get A equals to B. Okay. Make sense? Make sense or not? Yeah. So you need to be aware of this minimum maximum thingy. So they sometimes they always bring this uniqueness property. If it exists, there's only really one person can do it. Okay. So finally come to this. We can talk about this axiom here. So which is what Barry mentioned just now. We call this a completeness axiom or the least upper bound axiom. Okay. So what does this axiom want to do? This axiom says that every non-empty subset of the real numbers, which is bounded above, has a least upper bound. So it solves the existent problem. I throw the least upper bound into my set. Okay. So here the here, right? I can really replace with the. Why? Because just now we proved that it is unique. If you have one, that's the only one. Yeah, that one. Okay. And then finally we come to the big definition here. Real number is a set that satisfy three set of axiom. Field axiom, okay, so you can add you can plus you can multiply and then so on. And then order axiom, okay, we can deduce 1 greater than 0 from it. And finally the completeness axiom. And then this real number is actually what we call a complete ordered field. Okay. So real number is a complete ordered field. And there's an advanced theorem here. This is quite advanced. We won't prove it, but you can prove that any true complete order field are isomorphic. Okay, so what is isomorphic here means? So this is a bijection, first of all. Okay, you can form bijection. And then they respect some field structure. So what do I mean by respect field structure? So have you guys learned group homomorphism or not? Homomorphism learned or not? Not yet. Not yet learned. How many lecture already in group theory? 3? 3 lecture. I haven't gone into group homomorphism. Okay. Next time, I mean, in the lecture now, I will list out what does it mean by with respect to field structure here. So at the moment, you can think of bijection, but some extra structure on this bijection. Bijection, you know, right? a map that is 1 to 1 and 1 to 1. Okay. So this comes to a question of Joshua last time. So do we build real numbers by natural numbers, P&O axiom, and then Z, and then QR, and then go on to real? Or we just simply build real? Okay, so there are two ways to go about this. So one way is we can take the P&O axiom, okay, and then we put in group structure, addition, multiplication. But real, inside real, we have the few axiom, right? Exactly is the addition and the multiplication. So we can build like this. Okay. Or we can simply start with few axiom, order axiom, and completeness axiom. Build this real. And then we see that this real contains natural number. Why? How we find 0 and 1 here? Use the additive identity and multiplicative identity. Okay. But how we build 1 and 0 here? How we build 1 here? P&O axiom. 1 have to be inside my n first. And then I define what is 1 plus 1, 1 plus 1 plus 1, 1 plus 1 plus 1 plus 1, 1 plus 1 plus 1 plus 1 plus 1. Okay. Does it make sense? Okay. The 1 here is like, I make it inside here. But here, the 1 is special. It is the multiplicative identity. Okay. Does it make sense? Make sense? Make sense or not? Later we will make this even clearer. Okay, when we have a sequence. Okay, when we have sequence, we will make these two a way of building real number clear. So let me see what else we want. We finish at 1 o'clock, right? Okay. So yeah, let me see what thing we left with. 1, 2, 3, 4, 5. Okay, so let me tell you what's the plan for next class. We want to finish up the building of real numbers. Next, I will prove square root 2 exists. Okay, there's a real number which is called square root 2. And then I will show something about lowest property of least upper bound, and then Archimedean property, and then density of rational and irrational. So this chapter will stop at density of rational and irrational. What does it mean? Meaning any two distinct real number, you can find a rational number and a irrational number. So this is very strong. Huh? You know how strong is this? Every two real number, right? You can find one rational, one irrational. But rational and irrational is still real number, right? So that's I can find rational and irrational again. So every two number I can find one. Every two number I can find one. That's why we make our real line so connected. Okay. Number should be discrete, right? Every number there's a distance between them. Okay, but with this density here, we can feel the gap. We can keep filling the gap. Okay, until it is so close that these dots are together, almost together. You can't differentiate them already without microscope. Maybe microscope also cannot see. You need to go to electron microscope. Maybe electron microscope also cannot see. Okay. Okay. So that's why we draw this straight line like this, real line. So why we keep drawing real line like this? Because of the density of rational and irrational. Okay, we will stop tomorrow. This chapter will stop at this fact, and then we will start with a sequence again. Sequence. Okay. Okay, tomorrow we will talk about this. Tomorrow, right? Okay, see you tomorrow.
Hello. Hey, hello.